which is the incubator of OLA. So what's happened now is that the team from Sense and Y Labs, we work together on doing research, and we've been doing research since 2021. So if you go to our Hack and Be channel, and I'll share some of this documentation with you guys, you'll be able to find our research, and it will also run different algorithms in ZK, ranging from Halo 2 to different flavors of Plonk, to different flavors of Nova and folding schemes and subject schemes and so on. So for the talk today, it won't be hands-on. You can actually do things hands-on on your computer locally today with OLA, and I'll touch upon that at the end of the talk. But we're going to primarily be talking about data structures and how we're thinking about things in OLA. So we're going to start quite high level, and then we're going to look at some workflows, how we're doing things. Right, so I hope it's visible here. We had some issues here with the text being blurry. But from a high level then, what are we looking to do with Web3 and on an ethical level, what are we trying to do with OLA? So if we're looking at Web3 then, the premise is getting decentralized systems. And running these stacks aren't really optimized today. We have many centralized systems, and there are some flaws and pain points with them as well. And these are some of the issues that we are looking to tackle. And in order to do this, well, we have today achieved the decentralization of these systems, but I think we're lacking the throughput. Ethereum today has what, about 20 TPS, and if you're looking at Visa and MasterCard, they're pulling off 20,000 TPS. So we're not really there just yet. And if we're looking at the privacy sector, then with the public blockchains we have today, they are pseudo-anonymous, but you can still derive quite a lot from that data, which is fully transparent and public. And these are some of the issues that we need to tackle as well to ever have mainstream adoption on a decentralized tech stack. So the journey we're on, we have had different chains launch, and one example here would be Ethereum, and that's kind of how we started off, to have programmable smart contracts in a decentralized system. And after that, we started looking at scaling schemes. We had Plasma and so on, many ideas coming from Italian and the guys at Ethereum Foundation. We started seeing some optimistic rollups. We got some CK rollups, and then on the slide here, we're describing some of the CK teams in the space looking to achieve scaling. And then the third step, which we're looking to apply then with OLA, is also solving the privacy aspect. So we're looking to do scaling and privacy. And I'd say those are the two main pain points that we're looking to tackle with our design. So some of the issues that we're clarifying here is, well, once again, throughput. I mentioned that quite a few times now, so I'm not going to elaborate. But we're also looking to solve the problem, or it's not really a problem, but it's I'd say a quality of life, to have data ownership. Today on public blockchains, everything is transparent, and we want to put that data ownership back to the user. So in a scenario where everything's private, the user, him or herself, would have the option to share that data if him or her so wishes. We want to have everything in a one-stop solution. So we've had different schemes where privacy could be applied, like Monero or Tornado Cash and so on. But we want to have everything composable in one platform. So we want to give developers and users a choice whether or not they want to interact with a private or public app, and give them these options. Compliance, I think, is very important, and I'll be talking about this throughout the talk. We don't want to end up in a situation where we have agencies like the OFAC or similarly to come knocking at the door and try and shut things down. This is not a attempt to kind of go fully to the privacy side, but we want to build a very compliant tech stack and infrastructure that works with current regulation, with AML, travel rule, and so on. And also, as you guys may know, or some of you may know, we are building up of a UTXO system here because you can never achieve full privacy on things like Ethereum today. with the account-based structure of wallets. I'll be talking more about this in the coming slides. But we have our own smart contract language, and I will be describing that more in depth in the coming slides. So, the bread and butter of OLA, we're opting for ZK efficiency. There are teams out there who, if we're looking at the spectrum of Ethereum specifically, there's been a lot of discussion about equivalency and kind of making things work with Ethereum as is. We're going down the other route. We're looking at efficiency first, and then how can we be compatible with this? It's kind of like, instead of, if I have a Mac computer here that I'm showcasing you guys on now, if I want to run a Windows PowerPoint version on my Mac, instead of having Rosetta or some kind of virtual machine running on my computer to run the Windows version of PowerPoint, I would just rather swap out the computer and run a Windows computer from the back and run that natively instead of trying to patch it. And this is kind of the ethos we have in our team as well. So instead of trying to patch it up for Ethereum to make it work and be as equivalent as possible, we're opting for ZK efficiency, higher throughput. So some of the things we're doing here, if we're talking about efficiency, so first of all, with our language, OLA lang, it is a Rust-like, Solidity-like language. So if you know the syntax for Rust and Solidity, you're pretty much good to go. We are implementing what's known as the Prophet, and if you know about what hints are in Starkware, you'll be familiar with the concept. But it's basically about taking computations that aren't really ZK friendly during the calculation time and performing that. I'm going to call that outside of the VM. It's actually handled by the VM itself, but outside of the VM, we can prove that the calculation has been done correctly. I have some examples of this, so we'll be looking at that. But this is essentially a way to speed up and optimize for ZK efficiency. We're also using what's known as built-ins, and this is basically pre-compiles in Ethereum. So we have some wrapper functions, and you can call them in OLAlang, and this would be used, for example, given for bitwise operations or different hash algorithms. If you want to use like Poseidon, you would have that. And this would also kind of be called, like you would be calling Keshak in Solidity today. The next step is our compiler, which we've built. At the moment, that works for OLAlang. We are also looking to support Solidity here, and once we do that, you can basically plug and play your Solidity code directly and deploy that into OLA as a high-level language. The kind of rundown with the compiler is that it compiles down to a high-level IR, intermediate representation. It has some different steps here with semantics analysis and so on. Then that compiles down to our LLVM IR, and then that compiles down to risk assembly or OLA assembly, and then finally into OLA opcodes. We have some other, lean, I don't want to call it lean design here. So I think Ethereum has like 110 opcodes today. We have about 20 instructions. So we're trying to lower that overhead and not have that big of an instruction set. So everything is about making it as succinct and fast as possible. And there are some code optimizations on this in the compiler. This is actually not my area of expertise on what we're doing exactly there, but the premise is to use as few opcodes as possible to once again make it as ZK efficient as possible. So with the ZK-ZKVM itself, and by the way, this coin term ZK-ZKVM is just to be very clear of what we're doing. It's kind of become this coin term in crypto overall for your average user that ZK refers to scaling, whereas I think most of the people in this room knows that zero knowledge isn't really about that. So we're clarifying that we're doing privacy in one ZK and also scaling, so that hence that double ZK. But we have an ISA architecture, instruction set architecture. We're using RISC for that. And we deploy on the Goldilocks field. So we only support field operations, and word is a field element. This is abstracted away from the high-level language, so it won't be like the snarky JS where you have to define the fields in the language, but essentially, when we support Solidity, you also have your high-level smart contract assets and deploy that, so it's taken care of under the hood. And we're also swapping out, if we once again to the context of Ethereum, the Ethereum machine, it's a stack-based sequential machine. It's not very efficient for secret purposes to have a pop and a push output for every operation. So having a register-based machine with pointers in memory. So I just mentioned that we're deploying on the Goldilocks field here. Our proving system and the ZK backend is based on Starkey and Plonky2. And we've made some iterations of Plonky2 as well. So it is not your, well, the Polygon team is responsible for Plonky2, but it's not the official release from their GitHub repository. We took it, or we forked it, and made some modifications. Then we have some other tips and tricks up our sleeve in terms of making it more ZK efficient, such as parallel proving and using recursion. I will be talking about this on the technical overview slide. And then also hardware acceleration. We looked at many different schemes here on using GPUs, FPGAs, and ASICs. At the moment, what we're looking at here is doing GPU acceleration, and actually we have gotten some significant progress here. We're looking to speed up the NTT process, and I believe one of our engineers who's working on the hardware things said to me that for a data length of 2 to the power of 24, I think the graphics card was a RTX 460. We got it down to under 100 milliseconds for proving that data length of 2 to the power of 24 using the, I think it's called the Thule cookie algorithm, and we're looking at Stockton as well. So working on all types of optimizations here, once again for the end goal of having this very lean and efficient ZKVM. Right, so transactions. Is it visible, by the way, or is it too small? Should I zoom it in? You guys?
Please.
Okay. Yeah. So in Ola, if we're looking at these transaction types here, I need to mention at first, we're not looking to support EOAs, externally owned accounts, your traditional accounts that you have on Ethereum today, such as MetaMask and some of these wallets. Instead, if you are familiar with ERC 4337 or 4337, we have account abstraction. So off the bat here in Ola, we're just looking to have smart contract accounts. If you aren't familiar with ERC 4337, it's basically that your account, instead of just being this C phrase and a hash, it's actually a deployed smart contract on the chain. So the account itself is a smart contract. And there are some perks with this, such as that you could have your fees be paid in whatever token you want, in any ERC20 token, or you could have somebody else pay for your fees. So there are some reasons to why this might be better. You can store all your NFTs and so on in this one single place. And the 3 different accounts we have here then is deploy account, declare class, and invoke. So I think the deploy account one might be very obvious here. It's just about deploying your account. The design here, we took some inspiration of the concept of OOP, so object-oriented programming. And the premise is that you could, well then, most likely most users would want to have the same base layer of an account when you're deploying that. So a user would then once be able to send off the deploy account transaction, and you would have a node or a network of nodes that would store the bytecode for that instance or deployment of a contract, and then you would deploy instances. So that's the correlation between OOP here, that you can send off the transaction and then you deploy an instance of that. And this means that you can save on storage and so on. So you can have one transaction or deploy account, and then if anybody else wants a similar or the identical account with their own instance, you can just reuse that. And the same concept applies to the declare class, which is about deploying contracts. So if you want to fork any code, there are many examples like with AMMs, Uniswap and SushiSwap, and food name swaps for AMMs. You can save on storage by having one declared class, send through, and your statement was storage. So you would have an instance of that then. And you can add some properties as well. If you want a fundamentally different DApp, then you'd send off a new declared class function here. And invoke, I'd say, is the most important of the three. You can see here down in the bottom that you have the call data field. So this is the one that's actually sending stuff through to the blockchain. So both with the declared class and the declared count ones here. So if we take the declared class as an example, I would then send that through, but it would first be when the invoke is called that we're doing something here, we're deploying and interacting with the blockchain. Okay, swap slides, let's zoom in. Yeah, I'll zoom this in as well, as much as possible. So to the right here, yes, it says L1. I'll skip that part so we can zoom in on the other side. I think this will do. So, overview of the system. In Rollup, we essentially have a local virtual machine, which would be on your end user device, client side, and you would have node operators or sequencers who are responsible, the entity in the system, who is responsible for maintaining hashes and bytecode of what we just looked at on the previous slide with the transactions. So they would be the receiving end of that. So the blue stuff pretty much here on the slide. And they would also be responsible for sending this through to whatever is the layer above OLA. I could actually mention that OLA, it can be deployed on any blockchain. So if we wanted to, we could deploy on Celestia, who's downstairs, or Avail, which is another modular blockchain. We could deploy on Aptos or Ethereum. Even if we wanted to, we could deploy on CP-Sync Era as a layer 3. Essentially what OLA is, it's an encrypted execution environment. So what we're doing is batching transactions and sending a proof off somewhere that we've done X, Y, and Z. So everything in red on this slide refers to the privacy parts. So I don't want any of my data that I'm dealing with that's supposed to be private to be leaked elsewhere. It would be possible to relay that information, but in the design of OLA, you would then locally, so the red stuff is once again the local virtual machine on your end user device. I would calculate the local parts, and that would then, together with the public functions that are left to be executed, be sent off to the node, who would then look at the proof. So I would locally calculate a proof of the private aspects. I would send that through to the node provider, and together with the rest of the public functions be executed, and they would look at that to make sure that the signature is valid for the stuff that are done with the privacy, and then execute the rest of the public functions, and then send that off, batch together with the other transactions off to some layer 1, or the upper layer here. I'm gonna zoom in on a few things here. So here, this would be perfect. So some of the tricks we're applying here to have further ZK efficiency is dividing. It's kind of like a conquer and divide approach. So you have different things in the virtual machine that you need to prove, such as the built-ins, memory, CPU, and so on. And we're proving that in parallel. So it's more efficient doing this. If you think of the virtual machine and what it needs to prove as this big rectangular array of data, if you have one row, or like an Excel sheet, if you have one row that's particularly wide and many operations to prove, that's going to affect the entire table. So it's better to divide them into multiple smaller traces. You prove them in parallel because that's faster. And then after that, we recursively, as you see in the last step here, we recursively prove them all the way up to the top to one proof. It does say aggregating and folding here as well. At the moment, this is not true for Rollup. We have looked into many different schemes, and especially then with the different flavors of Nova, we looked at applying a folding scheme here. This is not present today, but it is feasible, according to our engineering team that we looked at this. And then finally, you would just send off that proof to layer 1. swap slides here. So looking then at the public and private logic again, we slightly touched upon this on the last slide, but you would have a user, and then if you're familiar with ERC-4337 here, you would have a user operation, or we call them user intents. The blue here represents the public inputs, and the red is just the private inputs. So we have our abstraction, you have your smart contract bullet, the paymaster stuff here, and entry pointer, by the way, also ERC-4337 specific namings, and it refers to account abstraction and the smart contract accounts. But the red stuff here is basically what I need to prove locally on my end user device. So I need to make sure that whatever UTXO objects I have, that I am allowed to spend them, first of all. And if that passes, I'm allowed to spend them, they are assigned to my keys. Then what I'm doing is I will be spending that, I'll create a new UTXO object. And then what's being sent through it is what's known as a commitment. And this commitment is just encrypted plain text data. So you can't really derive anything from that commitment. I will send a proof, this proof up here, and then the notes, together with the rest of the public functions and public data to be executed. And that's being sent through to, it says sequencer here. I've called that node today during the speech, but node or sequencer, which would then finish off the rest of the functions to be executed and generate a proof of the proof that I sent, the private proof, and the public functions that it just executed. And then we have some modeling here. So we just have some basic, I think it's EER modeling, so if you're familiar with permutation or any notation system. Some of the stuff we just looked at here, so this is just composability between the functions. I think we're actually maybe missing a function here. We're looking to add a internal type as well for function, not modifiers, but function types. But basically, if you're familiar with Solidity, very similar, private, pure, view, and public. And as we were just talking about, you can see here, if you're looking at going from public with this dotted line, there's an X here. X just refers to none or no, N is many, and one is one, obviously. So you cannot have a public function call a private function. And why is that? Well, that's because we've already generated a proof on the client side for all the privacy-related transactions. However, a private, if you're looking at this line here, the bottom line, a private function can call many public functions. Maybe you want to update some data, you have some DAP where, maybe an example given of that would be an AMM, once again. You want the trades to be private to counter things like MAV and front-running attacks and so on, but maybe you want the liquidity provision or maybe some update of the pool balance. You could have the trades be private, and that would be executed by a private function, but then afterwards you would send some info of what transactions took place in your AMM to update the balance, to showcase the balance still, and that would be handled by a public function. This here is quite important. Then we have our read and write access to what's known as the nodes tree root, or the private tree. And I have a slide about this, but this is a big difference to some of the other teams in the space doing privacy, like Aleo or Elastic. So, everything with privacy has been very controversial, I think, in the blockchain space. And I mentioned Tornado Cash and they got shut down. And at Rollup, we're taking this quite seriously. We're looking to design a compliance-friendly scheme. And I will be talking about how we go about this. Essentially, a big difference is in Aztec and Aleo and other teams looking at privacy, they have many different trees, amongst other the private tree state and a nullifier tree. And these trees are completely decoupled, and they have these two trees for the purpose of not being able to track anything. So the transactions are going to be completely hidden in the system. And in OLA, we think that you aren't necessarily, so privacy in itself is still achieved, even though you might be able to track these encrypted commitments I was talking about. So we aren't really compromising end user privacy. And I have a slide about this and looking at this. So what we're doing is essentially we are removing the nullifier tree, which, by the way, in the design of example given ASIC here, is an append only, and the same thing goes for the private state tree. So we have an updatable state tree here, which means that you are going to be able to backtrack in the blocks and see what has been spent and where in the system, but you're not going to be able to tell what kind of data that is. But I have a better slide showcasing that. Now, this might be small to see, so we'll take it half and half here. In the top here, you can see that it says membership and non-membership. You can think of this as the UTXOs being spent or unspent. The membership refers to as is it being a member of the tree itself. So what we have here is we have a public root, so that would be the public tree, which we looked at the last slide, and then we'll also have a private tree. Now, how this works in Rollup is that you would have maybe Alice over here, where it says Rollup. Alice has $100 in her account, and she wants to send that to Bob over here. So what would happen then in the system is that, so you can see this as well, Alice would then, publicly, we could see that Alice's account has been deducted $100, and that is visible. Alice would then create this UTXO object, the notes we were looking at, they're called notes by the way in Zcash, so there's no confusion. A note is a UTXO object. And she would then form a commitment of this note being created, and the commitment is what's laying in the mempool. But you can't really derive anything from this commitment. It's encrypted plain text data, it's just a string. So we can then see that, okay, Alice here, she's the sender, and she's sent something somewhere. So we know from the initial transaction that $100 has been sent. So we have CM, that stands for commitment. CM0 has been created. Then, if Bob wishes to send the UTXO of $100 to maybe to me, to Philip, then what would happen here is that Bob, who has the keys associated to spend that UTXO, he would go ahead and spend that, and we would have a new commitment, CM2 here, be created. And what you can tell from this transaction is nothing. So first of all, the commitment message, once again, it's just a string. You can derive no information about it, but we know for a fact that it's going to originate from Alice's first transaction. But we don't know the amount in it. But the premise here is that we are allowing for a more compliance-friendly environment. So you are able to track these assets. You may have actors like, I don't know, North Korea, that's an example, even come in and use your platform, and we are able then to still check where have these transactions taken place, but we're not compromising on the privacy of the users of a specific app. There is more in-depth to this as well. We're going to be talking about key management systems and functionalities. But from a tree perspective, this is fundamentally different from how things are in ASIC or in Aleo, as an example given. So how they go about this is they have two separate trees, and the big difference then is that they are completely decoupling them. So this link here between CM0 and CM2, it's not present, and there's no way of deriving where the funds have gone. But we're going down the route that we think this is not compromising the privacy, and at the same time, it's bringing a more compliance-friendly environment to talk to regulators and so on. We're still zoomed in.
Question about that.
Yep.
So you're able to see, you're not able to see the content of the transaction or even necessarily who it went to, but you can see who the source was, is that what you're saying?
Exactly. So you can follow the source, and then so since this is updated, you can also see that this is the same leaf. See, commitment 0.
Right.
It's the same leaf as commitment 2 here.
So what behavior can then result from that? Can we say like tag certain UTXOs as being poisoned, and so therefore we would not want to take transactions from them, or can we prohibit certain systems from being able to conduct like now that opens up like what censorship or actions can we take as a result of that knowledge?
So it's a very good question, and I would say that yes, it is possible to look at this specific one. Let's say that okay, something fraudulent may be, or we're suspicious that something fraudulent is referring to this transaction here from between.
Alice is actually 100 North Korean hackers in a room.
Yeah.
Right.
Yeah. Exactly.
We know that now.
Yeah. So then you would have the knowledge that from between this step here, you know that okay, something shady has happened here, and you can basically backtrack. Then you're backtracking through the blocks.
Mm-hmm.
So the state we're looking at here is in block Y, and the state here is in block X, and you would then look at you know for a fact that it is this specific leaf in the tree in block X that you don't want to include,
Which is represented as UTXO, right?
Yeah.
Okay. So we would just say we're not going to accept transactions that are poisoned by this UTXO.
Yeah.
Okay. Isn't that the problem that all privacy people have about this?
Well, so it depends on what you define as privacy or private. Of course, you're not having
specifically censorship resistant.
Yeah,
Right, that's the issue.
Sure. I think the blacklisting of a UTXO, you would need to have something, very tangible to go to that depth. But yes.
Okay. All right. Thanks. Let me try to understand.
Yeah.
Can I ask a question?
Mm-hmm.
For like transfers, right, it's going to like split the UTXO into like two. The graphic depicted the UTXO being in like the same place, but like a transfer always, there's like the remainder.
Yeah, sure. If you have some change or something, that would be split. Yeah.
Okay.
And also with the UTXO structures, so how there are so how we're adding the programmability to the privacy, which is one of our main pitch, programmable privacy. If you think of the existing UTXO system out there, like Zcash or Bitcoin, essentially you have this UTXO object, and what that consists of is this: you have an address, like an owner. You have a value field. It's not some encapsulated satoshis. That could be 1 or 100 in your example here. And one of the things we're adding as well is this data field, and that's also how it's different from Zcash or Bitcoin. And this data field is what makes it programmable. And this is an encrypted state essentially. It's a state referring to some depth, and that's what's shoved into the smart contracts. So this state field can contain a lot more information instead of just having that value field. And in this state, that could be, it can contain any arbitrary data from structs to whatever that may be. And in that state, you could have your changes, and if we then have some change, as you mentioned, you would have a split here. But in this scenario that we were looking at now, that I simply described, we just sent 100 all the time. Hence why the tree was just updating one single leaf. But if you have some change, I would send that back to myself, and then I would need to occupy some more memory and allocate that to something else, right? But why in the example here would we just send 100 all the time? Just taking up one.
Yeah, I guess to be like more specific, the traceability, the way you get traceability is through the actual transactions. It's not like the location
Exactly.
in the tree, right?
So the big difference is that they're linkable. They're linkable, right?
Yeah,
To
the
the
commitments are the same.
Yeah.
You don't have a nullifier set. You
Yeah.
just have commitments, and then you produce these commitments and spend the commitments
Exactly.
the same way.
Exactly. It's kind of how you can backtrack UTXO backchains today in transparent systems. So a UTXO can be backtracked to the genesis of that UTXO in transparent systems. But you're backtracking encrypted plain text data, so you can't derive anything from that. You can only see where it originated from. In our example, that originated from Alice.
Yes, that makes it kind of interesting to build wallets for this, does it not? To be able to say like what my account balance is.
Yeah, we're going to talk about that now.
Glad I could help.
Yeah. We are building up of the work of Zcash here. So the Zcash, they started off with the namings are from like I think they're called sapling to some other tree synonym, and then to orchids, so flowers and so. And they essentially have a entire key management system here. So if you think about your traditional wallet, you have some seed phrase and you run some hashes on that, and that's how you derive your private key, and you run some further hashes, and then you get your public key. But in here, in this Zcash model, there's many different steps and many different keys in between. So we have taken some inspiration here, and I'm going to zoom in again, so this is truly visible for everybody. There we go. So to the right here, we are looking at the account keys for one account. In OLA, we were talking about previously that the word is the field element, and we only support field operations, etc. But essentially, you don't have a seed phrase that's words. You have a seed phrase that's a random number, and that forms your secret key. And this is basically the seed to generate other keys. And then you have this spend authorizing key, which you can think of as being the private key in the system. Here we have, if we go back to the topic of compliance and regulatory concerns, we have what's known as a viewing key. And I want to highlight that a viewing key is not enforceable. This is a private key still, so the end user would hold that to him or herself. And you have the option to share this key. So some example given could be that if I want to prove to Alice that I have indeed paid Bob for a single payment disclosure, I could do that. If I want to maybe for regulatory or tax purposes share my entire transaction history, I could give them my full viewing key and tell them, hey, here you go, these are my transactions. And this kind of design, also going back to empowering the user, is important because maybe you have teams like chain analysis, and they base their entire business model around scavenging on-chain data, which is free today. They can just do that however they like. But if everything's private, if everything is in commitments, well, they can't do that anymore. But maybe they are willing to pay for my data to draw those insights. And I can tell them, hey, well, hey guys, for $5 a month, sure, go ahead. You can do whatever analysis you want. So the viewing key is used to view user assets. And then to your question, well, how do you know what UTXOs belong to what wallet? Well, you have what's known as the graph key. And this is basically to filter and go through the tree and look what UTXOs actually belongs to me. And then, for greater UI, UX purposes, you will just bundle that together and calculate the worth of those assets in your wallet. So the wallet wouldn't say like, oh, you have these different objects all scattered around. It would be more like, well, we aggregate that and give you the sums. Well, you have this amount of value. So from a UI, UX perspective, this is a non-issue. And we also then have, so when these newly nodes are generated, the nodes also have keys that are connected then to your private key. So if we're looking at the top here, and I guess this is the only important thing, that when I'm then, if Alice, going back to our example, if Alice sends something to Bob, that would incorporate knowing Bob's public key previously, so they would create this shared key so that Bob can also decrypt this commitment message. Because if I send this commitment to Bob and he has no way of decrypting it, then that's not useful at all. So basically, that entails ahead of that transaction taking place.
Your computer is.
We have an error. We did. This is not my computer, so it's in Chinese, but I think we have an error. Okay, we'll open that up again. Yeah, my Chinese, by the way, is non-existent. I know a few words. But yeah, essentially, it is to the recipient, you would include their key in that transaction, so that they have a way to decrypt that commitment as well. Because otherwise, that would also just mean that it's plain text encrypted data for them, and they couldn't really do anything.
So I would think, would it be correct to describe these keys as really, these are permission tokens to allow me for the scope of this wallet address, forever and ever, amen, all of its holdings, right? This is not something that's revocable because it's tied to the wallet.
It is tied to the wallet. So these are, these are the account keys to your specific wallet.
Right, and so they're not tied to any particular UTXOs, they're tied to the wallet, they discover the UTXOs and let you discover your assets.
Correct. However, the key we looked at up here, the shared key, that's connected to the UTXO as well. Because you can see here that we run some hashes here to the right here, which is the node is the UTXO, right? So that's to a specific UTXO. But these keys to the left here is only for the wallet.
Is this gonna be the,
Then about the language. So Olalang, it's well, the machine is Turing complete, so you could deploy any arbitrary logic. We are also looking to have a high level of abstraction here. So how we go about the design of the ZKVM itself is, instead of taking these ZK components and shoving them into the language, making it a DSL, we're looking to go more down the GPL approach and having this general purpose language called Rollup. And all the ZK stuff is kind of like, we take that and we abstract that away and we shove it into the hood of Rollup. It's kind of like if I walk into this room and I want to turn the lights on, I just flip the switch. I don't need to care about how the copper wiring looks behind the wall and how electricity is funneled up through the street into the building. It just works. So, and how we are achieving this is that we have constraints or gates that will constrain the virtual machine. So it caters with our general purpose registers for any program to be compiled through the circuits. It's quite dev friendly, as we touched upon, Rust or Solidity, and you're good to go. And then we spoke about some of the ZK friendly stuff, which I'll be showing an example of. So here is an example of the Prophet. We actually don't have the code of the Prophet here, but I'll show you what we're looking at. So to the left here is the native approach of calculating a square root. So we have 7 lines of code. You need to run a for loop here, and this is going to result in quite a few opcodes. And the other way of doing this would be to use the Prophet. So this is just a wrapper function for the Prophet here. But in the top here, you would see us just calling marked in yellow here, which is the wrapper function. And if we look at that then, so what would happen is we would, in the green mark here is calling the actual Prophet code here, which is not visible on screen. So the actual Prophet code is not visible here, but we would call the Prophet code, which could be maybe this could be a Python script or whatever that may be, which would give us a result. And then you can see on line 11 here and 13, we're using built-ins to just assert that the calculation has been done correctly. And by doing this, we have done some benchmarks. So with the native approach, to calculate the square root 1,000 times, that took us 4.5 seconds roughly. And the proving time was about 163 seconds. Whereas when we used the Prophet, this was way faster, 58 milliseconds, and the proving time was almost 10x faster in 12 seconds, or even more than that. And it's also a much smaller trace size, so making very succinct and speeding things up. So the square root here is one example, but this is a library of different implementations that the team of Ola at the moment is providing. But the intention is that developers in the future can come in and write their own Prophet implementations. If they see a good fit for something that's CPM friendly, that they could write better or faster, they could just open a pull request with a suggestion, and that could be brought into the list. And essentially then that would mean that we would have a wrapper function of that, and developers could just directly in their code, in yellow up here once again, call that Prophet implementation.
So a profit, is this really just extending a new intrinsic into the system?
It's kind of like, do you know what hints are in Starkware?
No, I don't.
Okay, so it's basically us taking calculations, well, so calculations, primarily calculations that are ZK unfriendly during calculation, but friendly during verification. There could be parts that are both unfriendly for verification and calculation. But basically, us taking that outside of the VM, it's actually handled by the VM as well, like that program, but outside of that context. So that can be done in a script in some other high-level language, and then that's much faster. And then you need to verify that the calculations been done correctly. That's essentially what it does.
Is it because of the nature of how the profit code is implemented, or the fact that you've declared it as a trusted intrinsic, so I don't have to track as much information about it in the trace?
It's because you don't need to generate a trace for it at all. So
because it's kind of trust, we say this becomes this, and we trust that fact. And
exactly.
Okay.
So when you do this, if you've done it natively, we would generate all these opcodes here, and we would need to prove those opcodes in the trace that everything's been done correctly. So
the major trace savings here was the fact that we eliminated all iteration, and so there's a massive reduction in what needs to be traced.
Yeah.
Okay.
And then we just need to prove that, well, this was done correctly.
Right.
Yeah.
All right.
So is it a set of predefined profits, or me as a developer, I'm able to implement my own, I don't know, Rust, and use it in my own code?
Yeah, so at the moment, how it's done is that we maintain that list of profits, and in the future, what we're looking to do is to open this up, so any developer can come in and give suggestions to this official list. But you could also just write your own if you wanted to, but then the intention is that if you write this magnificent code, that you would just send this to us, and we could include this so anybody could use it. That's the intention. But yes, you can definitely write your own without going through our official channels. But we want collaboration here. So if you write something great, then that would be good, so we can include that officially to everybody. And this should be the last slide, where I have the roadmap as well. Okay. So we have some docs. Everything's open source. We have a few local branches, so maybe not everything. Don't quote me on that. But 95% is open source. We love to find collaborations. We love to see devs build on Ola. In the future, we are going to host more hands-on workshops. And I will actually, guys, show you that you can actually be hands-on with Ola today already. But we haven't really fine-tuned our documentation so that this would be a smooth experience. But what you can do already today is that you can download the prerequisites like Rust, LVM, and so on. Download the virtual machine, the ZKVM FPU CS they've done, and you can write a simple program in Ola today locally on your computer, and you can generate a proof for this, and you can verify that proof yourself. So I will show you that. We can hop over to the GitHub repo and briefly check that. And I'll just touch upon the roadmap real quick. So we did a POC earlier this year, and Q3, which is now starting July. You can, what I just mentioned, have the internal tested locally on your computer. And what we're looking to do now is we're fine-tuning the compiler, we're working on the hardware, and making sure that we get a better developer experience with the primarily documentation. We're working on a book-like format to make sure that devs have everything that they need to write programs in Ola, basically. And we're looking to launch this in Q4. But let's hop over to GitHub real quick, and I can just show you. So our GitHub handle at the top level is just Sin7y, which is the labs entity. And we have many different repos here. So if you want to check out the proving stack or how Ola lab is done, everything is here, so you can find that. We also have the workshop repository that you can go into. And you have some of the prerequisites here, which will take you to the Ola lang repo and so on. You can download everything that you need for the language and the VM, etc. And then we have some basic examples here. Here it's a Fibonacci program that you can run, very simple, basic. You will just compile it, and then you will generate a proof. You have all the steps here to do this. And basically then, what you've done is you wrote a Rollup program, you have generated a proof for it, and you have verified it locally. So yeah, if you guys have any more questions, I'll stop here. Take any questions?
Maybe downstairs, the questions.
Yeah. Yeah. We made a full hour almost. Jesus.
Yeah.
I ramped it up a long time. Yeah. So if you have any questions, I'll be downstairs by the booth, floor 0 or is it 1? Floor 0.